6-4 Applications of Linear Systems. So we have learned 3 ways to solve a system of linear equations: graphing, substitution, and elimination. We are going to take those 3 methods and apply them to real-life situations. Oops. All right. Oops, sorry. Here we go. So basically, before we begin, our 3 methods, like I already mentioned: graphing, substitution, and elimination. Graphing. You want to use graphing when you need a visual display of the 2 equations and that solution or that intersection point. Also, if you want to estimate the solution, graphing will allow you to do so. Substitution is when you already have one equation that's solved for a variable, or if it's pretty easy to solve for one of the variables. Substitution is going to be your best and quickest way to find the solution. Elimination, remembering when the coefficients of one of the variables are the same or opposite, then you can add or subtract the equations. And you would also use elimination when graphing or substitution isn't a convenient option. All right, so we're going to talk about 3 applications of these systems and what the solution would be used for. So first of all, we're going to talk about a breaking point, a break-even point. A lot of times with businesses, when they are selling a product, they have to pay a certain amount of money to just be able to make the product. And so all the expense they put into the product and then the money they make, they usually hit a break-even point. We're going to learn how to find that. So here is our example. A fashion designer makes and sells hats. The material to make the hat costs $5.50 per hat. The maker or the designer sells the hats for $12.50, so he's making a little bit of profit. The designer spends $1,400 just on advertising. How many hats must he make to break even? Or sorry, to sell to break even. All right, so we're going to write a system of equations. First, we are going to write an equation just for the expenses the fashion designer has to make. So Y is going to be the number of dollars that he either spends or makes. So first, for expenses, this is how much he's spending. It is $5.50 per hat just to make it, plus he or she spends $1,400 just on advertising. Then, for income amount that they make $12.50 for every hat that they sell. All right, so we have a system of 2 linear equations. I'm going to use substitution since this equation is already set for the variable y. I'm going to plug 12.5x into this equation. So y is right here, which I'm replacing. 12.5x equals 5.5x plus 1,400. Subtract my 5.5x, I get 7x. Divide by 7, x equals 200. Since x stands for my number of hats sold, I can stop right there. And my answer to the problem, this fashion designer would need to sell 200 hats in order to break even. All right, second application problem. It has to do with a mixture. All right, a dairy owner, produces low-fat milk containing 1% fat and whole milk containing 3.5% fat. How many gallons of each type should be combined to make 100 gallons that is 2% fat? So we're making a mixture. First, I just want to know how many gallons we're dealing with. So X gallons of 1% milk plus Y gallons of 3.5. We want to have a total of 100 gallons. So that's our first equation. Second equation, the fat content. My number of X is 0.01. 1%, as when we write a percent, we move the decimal 2 places or divide by 100. So 0.01 times the number of gallons plus 3.5. So 0.035 times Y amount of gallons equals we want our mixture to be 0.02 times 100, not for 100%, but because we want 100 gallons of this 0.02%. So remember that this 100 isn't standing for the percent. A lot of times we multiply percents by 100. This is standing for the amount of gallons we want of the 2% milk. So I can easily solve easily solve this equation for a variable. X, I can subtract the y over, so I have 100 minus y. All right, and now I'm going to substitute this equation into the second equation. So I'm going to have 0.01 times x, which we know is 100 minus y, plus 0.035y equals, and 0.02 times 100, I can do the math, is 2. I can distribute 0.01 times 100 is 1 minus 0.01y plus 0.035y equals 2. I get 0.025y equals 1, y equals 40. And then my final step is to plug 40 for y back into an original equation. So x plus 40 equals 100. X is going to equal 60. So the owner should mix 60 gallons of low-fat milk with 40 gallons of whole milk. The third application problem has to do with solving a wind or current problem. All right. When a plane travels from west to east across the United States, the steady west-to-east wind acts as tailwinds. In other words, if you are in a plane flying on a vacation, if you go from west to east, you can calculate your speed by taking the airspeed plus your wind speed, and you'll get your ground speed. If you're going the opposite way, east to west, you do airspeed minus wind speed equals ground speed. You'll go a little bit slower. So using that, we're going to set up two equations. A traveler flies from Charlotte, North Carolina to Los Angeles, California. At the same time, another traveler flies from Los Angeles to Charlotte. The airspeed of each plane is the same. The ground speeds are shown below. What is the airspeed? What is the wind speed? All right, so let A equal the airspeed of the planes. Let W equal the wind speed. I'm going to set up two equations. My first one, the airspeed plus the wind speed equals 550. I got that from this plane here going west to east. And my other equation is my airspeed minus my wind speed equals 495. And I got that from this plane going east to west. Looking at these equations, I can do elimination very easily because the coefficients cancel each other out. I have A plus A is 2A. 550 plus 495 is 1045. Divided by 2, the airspeed equals 522.5. Once we have the airspeed, we just need to solve for the wind speed. I can plug it into either equation, and when I do, looks like the wind speed will equal 27.5, and I got that from plugging A into either of these two equations. All right, I would like you to attempt 1, 2, and 3 of the lesson check and bring your answers to class.